Ladies and gentlemen, hello, hello, hello. Mr. Din here once again with another lesson for you guys. You know, it's supposed to be getting warmer, but my apartment stays cold when it's supposed to get warm and warm when it's supposed to get cold. And so I'm still bundled up, feeling the coldness. How's it going? How's it going, everybody? I'm talking to nobody, but hopefully when you're watching this video, you know that I am concerned for you, wondering how you are. Today we're going to finish up our lesson about cladistics. Started it last time. Let's finish it up. Alrighty. Let's take a look. We are looking at this. Okay. Here we are on lesson number 9, cladistics part 2. First thing on the agenda is to have a brain jog number 9 about clades. This goes on page 34. Please submit that. Number 2 is a continuation of our cladistics explanation. Submit that as well. And finally, I want you guys to be practicing how to do clades on a whiteboard. Now, I don't want you to simply reproduce our notes. It's not going to help. What I want you to do is I want you to put cladistics into your own words. Try to explain things on the whiteboard in your own words. That's really the only way the whiteboard works. It's no point in just reproducing my notes and then trying to memorize that. Run the information through your own brain. Okay. Number 4, we're going to have a quiz next week on Zoom. So for you guys, it's going to be next Thursday. It'll be our last quiz of the semester. Then you guys will take your semester final, which we will discuss tomorrow on Zoom. That's the agenda. Let's take a look at our bills. Where the heck are we? That's the wrong thing. Here we are. We're on page 34, so Brain Jog 9 will go on page 34, and on page 35, we're going to finish up our explanation, as I said earlier. With that, let's go back to our explanation here. Where are you? Where are you? There you are. Take a look. Last time I introduced to you something called a cladogram. It's a map. It is a map of evolutionary history. We can actually separate which organisms are similar to each other and share a common ancestor by putting them into something called a clade. A clade is a group of modern species that have shared a common ancestor in the past. As you can see in this example cladogram, C and D species are so close together that they shared a common ancestor in recent history. The biggest clade you see within this cladogram includes the organisms A, B, C, and D. All 4 of these species belong to the same clade because they all have similar characteristics, similar DNA, and of course descended from the same common ancestor. We gave you a real example last time of a clade called dinosaurs, archosaurs, and finally the clade squamates. Cladograms are not unchangeable. They can shift according to new DNA molecular evidence. As you can see, these cladograms can move if we find more evidence to build our knowledge. What I'd like to do today is to introduce 2 other ideas to you. This should not take long. You can take your markers out and your flashcards. Let us look at 2 other ideas. Down here, I'm going to introduce to you something called a molecular clock. I remember being introduced to molecular clocks back in college. I didn't know what the heck they were. I'm like, a clock? Does it tell time? A molecular clock is telling when 2 species diverged. based on near constant mutation rates. That is what a molecular clock is. Doesn't make a lot of sense right now. It makes a little more sense when I introduce an example to you. Let me read it out loud. A molecular clock is a clock that tells you when two species have diverged in the past based on something called a near constant mutation rate. Okay, the best way to demonstrate this is to just give you an example. Okay, so if we examine the DNA of a human, let's say, and we compare that to the DNA of a chimpanzee, you will find that the human and the chimpanzee have nearly identical DNA. They're pretty dang close, it's like 99% or something. What you find, as an example, this is not a real number, but what you find is that there are two differences in the DNA sequence. Just two. Again, these are made up numbers, but to make it easier for you, just two differences. Okay, so you look at those two differences and you say, all right, well, if there are two differences, can I deduce how long ago these two modern species shared a common ancestor? Can I do that? Can I look back in time and tell when these two species actually diverged? And the answer is kinda. Molecular clocks are based on an assumption that mutations occur at near constant rates. So maybe a mutation occurs every 10,000 years. Now, when I say a mutation, I mean a mutation that is actually carried on in the species. Sometimes you get random mutations, but they don't really affect anything. I'm talking about a mutation that does actually affect stuff. So, okay, let's do the math. If a mutation, in this example, occurs every 10,000 years, and there are two mutational differences between a human and a chimpanzee, how many years in the past would we expect these two modern species to have diverged? Well, you just do the math. One mutation every 10,000 years, there are two mutations present. 2 times 10,000, you can expect these two species to have diverged 20,000 years ago. Now, is that accurate? No, it's just an example. Chimpanzees and humans probably diverged 500,000 years ago-ish. Anyway, that's how we know approximately when two species have diverged in the past. So we can do another example. I can just say it out loud. Let's say you're looking at a chimpanzee and a horse. Chimpanzees and horses have 134 mutational differences in their DNA. And the molecular clock shows that every 1,000 years, there's a new mutation. That's pretty fast, but I'm just making some numbers up. What do? 1,000 times 134, you're looking at 134,000. Now, this can only be done with comparing different species to each other. So there you go. That's called a molecular clock. It's a pretty cool idea. Do you guys know the movie Anastasia? The Grand Duchess. I have some songs stuck in my head. I was listening to them earlier as I was grading. Anywho, I have one last idea to introduce to you guys. This idea is the difference between something called an analogous trait and a homologous trait. Now, we talked before about how traits can actually be put into a cladogram along its spine. You can even put a trait up here if it evolved through an adaptation. Well, there are two kinds of traits that we can apply to a cladogram. And remember, these traits are phenotypes. We have something called an analogous trait and another thing called a homologous trait. Now, the difference here can be quite tricky, so I want you all to pay attention. Two rings. Let's start with the easy one. Homologous traits evolved together from a common ancestor. Okay. If you see something in nature where you say, that kind of looks similar, did that trait evolve separately from each other, or did it evolve from a recent common ancestor? I'll give you an example. See these? The nostrils. We see nostrils in all kinds of animals, do we not? Horses, apes, dolphins have nostrils too. So do whales. They have nostrils. Rodents have nostrils. We say, did that trait evolve separately from our nostrils? Or did we all once share a common ancestor with mammals? This would be considered a homologous trait because we are all descended from a recent common ancestor. That is a trait that we have adopted from a common ancestor that moved from the water to the land, which we'll talk about later. It's called tiktaalik. Okay, an analogous trait is a little bit different. An analogous trait is a trait that evolved independently, but they look similar. A good example of this class are wings. When you look at a bat, like a vampire bat or something, it has wings. When you look at a bird, it also has wings. But the wings of a bat are different from the wings of a bird. They are analogous, but not homologous. Birds and bats do not share a recent common ancestor. The wings of a bat actually look a lot similar, more similar to the bones of your hand than they do to the bones of a bird. So we say that the trait of wings is an analogous trait comparing birds to bats. That's an analogous trait. So I hope that those two examples really drove home the point, the differences between analogous traits and homologous traits. Let me summarize today. A molecular clock is a clock that can tell us how far in the past two modern species have diverged from each other, under the assumption that mutations generally occur at near constant rates. We can actually do some quick math with it, quick math. We can say that, okay, if a mutation occurs every 10,000 years and there are two differences between two modern species, you just multiply the number of differences by the number of years and you get an approximation of how long ago these two species diverged. Second idea is the difference between analogous and homologous traits. Homologous traits are ones that we share with other species, but we descended from a recent common ancestor. And an analogous trait are similar looking traits, but they actually evolved independently from each other, like the wings of a bird and the wings of a bat, and the wings of a butterfly while we're at it, and the wings of a moth, so on. All these two ideas share similarities between the cladograms that we talked about before. They all kind of go together because the homologous or analogous traits can go directly on the cladogram, and the molecular clock allows us to know how long a particular line is. So I'm going to stop that share. I hope you guys are doing well. The last thing we're going to do is a whiteboard diagramming activity that I want you all to do on your own. Practice this. Cladistics is hard. It's a lot to explain. It's a lot of words you have to use. So give it a shot. Let me know. Miss you guys. Peace.